Okay, Chapter 3, Section 4, Proofs with Perpendicular Lines. So we're going to be doing some distance to start the section off just a little bit. And so we're going to pull up some graph paper. You might need a little scratch graph paper there um, in your screencast notebook, and you can tape it or staple it or however you want to put that in there. But we're going to find some distance. And so I'm going to set up a graph here just a second, and I will be back with you momentarily. Okay, so what we're going to do is we're going to find the distance from point A, which is this point, is this point right here, to the actual line segment BD. And BD is the line that stretches across. So we're going to go from A and find where our perpendicular line is, and that appears to go to point C. This is example number 1 on page 134 if you'd like to follow along. So distance always has to be perpendicular. It's like standing up and getting your height taken at the doctor's office. You always stand up and you're not sitting in a chair at a different angle. So we have to find that perpendicular distance. So we're going from negative 3, 3 to 1, negative 1. And so now we need to recall our distance formula. Distance is x2 minus x1 squared plus y2 minus y1 squared. Again, we square those so we have positive values inside there because distance always has to be positive. So just working through this, our x sub 2, which would be our x value of our second point, is going to be 1. Then we're going to subtract a negative 3. Our y2 value is negative 1. And then we are going to subtract the positive 3. So that's going to be 1 minus a negative 3. That's going to be 4 squared. Negative 1 minus 3 is negative 4 squared. So that gives me the square root of 16 plus 16, which would be radical 32. That radical 32 is going to come out to be approximately 5.7. So a little visit from the distance formula from way back when, finding distance from a point to a line. Okay, so I'm going to do examples of 3 of the theorems that you're going to see. The first one is going to be 3.10. And basically what that says is if I have a line that intersects another line, and both of those are congruent to each other, if both of those are congruent to each other, and that's a linear pair, then they would both have to equal 90 degrees. So let's say this was AB, C, D. In this case, if ABC and DBC form a linear pair and they are both congruent, as the little arcs say, so angle ABC is congruent to angle DBC, then that means that AD is perpendicular to BC. They intersect to form a 90-degree angle. And that's theorem 3.10, the linear pair perpendicular theorem. Then we have 3.11. Okay, and 3.11 is the perpendicular transversal theorem. And it says if you have a set of parallel lines and you have a transversal that is perpendicular to one of the lines, let's call this line A and line B. So if you have a transversal that is perpendicular to one of the parallel lines, then it is also perpendicular to the second parallel line. So that would be 3.11, the perpendicular transversal theorem. Again, just to read that to you, in a plane, if a transversal is perpendicular to one of the two parallel lines, then it is perpendicular to the other line. So let's say I named that C. That would mean that C is perpendicular to A, and C is also perpendicular to B, but only because A is parallel to B in the first place. And then let's finish with 3.12. And 3.12 is the lines perpendicular to a transversal theorem. So in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So this one kind of looks like the one before, except that's our transversal. And here are our lines. I feel like we're about to play a big game at tic-tac-toe, but we're not. So again, let's say this is, we'll call this A, we'll call this B, we'll call that C. C is our transversal in this case. And so the two lines are perpendicular to the same line. So if they're both perpendicular to the transversal, then that means that they are parallel to each other. So in this case, A is perpendicular to C, B is perpendicular to C, but also A is parallel to B. And that is 3.12, the lines perpendicular to a transversal theorem. And that is chapter 3, section 4, proofs with perpendicular lines.